The question of how the universe began has fascinated humans across cultures and civilizations for thousands of years. Ancient myths and philosophies put forth imaginative explanations, while modern scientists have attempted to determine the origins of the cosmos using physics and observation. As human knowledge expands, our understanding of the early universe continues to evolve. In recent decades, an overarching explanation called the Big Bang Theory has emerged among scientists to describe the beginnings of space and time as we know them. However, mysteries and debates remain regarding what happened during the initial moments after the Big Bang, as physicists push closer to an elusive theory of everything that may one day reveal new insights about the emergence of the universe. This article will explore the current scientific consensus surrounding the origins of the universe, as well as the continuing quest to uncover its beginnings. The prevalent theory for the origin of the universe among cosmologists is that it began approximately 13.8 billion years ago from an enormously energetic event called the Big Bang. In this model, the entire mass of the universe existed as an infinitely dense, searing hot point called the singularity before rapidly expanding and cooling into the more diluted, cooler cosmos observed today. The concept of an expanding universe originated with mathematician and astronomer Alexander Friedmann in 1922. Building on Friedmann's work, astronomer Edwin Hubble later discovered through observations that distant galaxies appeared to be moving away from Earth at speeds proportional to their distance. Hubble realized that if the contents of the universe are currently moving apart, they must have once been compacted together. In the late 1940s, physicist George Gamow recognized that radiation left over from an intensely hot early stage of the universe might still be detectable. In 1964, astronomers Arno Penzias and Robert Wilson serendipitously discovered a faint radio signal permeating the sky from all directions, consistent with Gamow's postulated background radiation left from the aftermath of the Big Bang. Their cosmic microwave background, CMB, discovery provided compelling evidence for the hot Big Bang model. Through subsequent decades, astrophysicists and cosmologists have fine-tuned the parameters of the model as space observatories revealed subtle temperature differences within the ancient radiation. Extremely small variations in the CMB are now understood to reflect tiny inhomogeneities in the infant universe, which seeded later density fluctuations resulting in contemporary large-scale cosmic structures. The current standard model of cosmology has been extremely successful at explaining the broad evolution of the universe over the past 13.8 billion years. Despite its general success, aspects of the inflationary Big Bang paradigm have been difficult to test, and observations have continued raising challenging questions. Efforts are ongoing to search for definitive corroborations of cosmic inflation. Additionally, physicists have been unable to reconcile gravitational physics with quantum physics in order to describe the universe at the intense densities that existed during the initial moments after the Big Bang. At T-0, the instant of the bang itself, conditions so utterly different from the present cosmos existed that known laws of physics likely break down completely. Physicists are still working to discover a theory of everything called quantum gravity that can describe behavior at these earliest moments. Promising hypotheses have been put forward about the universe's opening state, such as eternal inflation, string theory landscapes, and speculative quantum bounce models, which avoid the problem of infinite densities altogether by hypothesizing contracting universes preceding each Big Bang. However, considerable theoretical work and additional observational evidence is required to select among imaginations. Ultimately, closing gaps in describing the emergence of space, time, matter, and energy directly from the quantum fuzz at the bang lies a horizon beyond what has so far been discerned through physical models and experimental data. Yet possibilities wait to be unveiled toward unraveling the cosmic riddle. Our comprehension of the earliest history remains incomplete. Additional undiscovered physics might expand understanding of the primordial universe's dynamics in the future. Upcoming observatories will offer novel glimpses, progressively illuminating the scientific narrative back towards Genesis. The immense aeons preceding humanity make direct witnesses to creation unattainable. Nevertheless, intrepid 21st century researchers relentlessly narrow known unknowns through bold new apparatus and analysis augmented by cunning inference. Space-based surveys scan relic photons from the hot, dense epoch when stars were unformed. Data-driven computations reveal turbulent conditions, which once etched seeds materializing downstream as resplendent galaxies. What initiated existence poses limitless theoretic possibility and introspective awe, inspiringly linking impersonal cosmic happenstance to our inhabited world through deep time. While daunting riddles endure, compelling revelations awaken flickering cosmic consciousness within our earthly realm. Still greater revelations undoubtedly await regarding the beginning, which set our wondrous universe into motion. Don't forget to like and subscribe to our channel so you don't miss new videos.